This video is on solving equations that have variables on both sides of the equal sign. You should be on page 154. When you solve an equation that has variables on both sides of the equal sign, what you need to do, and I highlighted it here, you need to collect the variable terms on one side of the equal sign and the constant terms on the other side of the equal sign. So let's think about that real quick. A lot of vocabulary here again. Remember, variable terms would be things that have variables attached, like 3x would be a variable term, or 5y, or 3z, stuff. Things that have a coefficient and a variable would be called variable terms. Constants are numbers without a variable, okay? So these instructions are telling me if you have variables on both sides of an equal sign, the first thing we should concentrate on is getting all the variables on one side of the equal sign and all the constants on the other side of the equal sign. The book shows you a couple examples of this. I don't want to just hash through these. I'd like to just do some of our own. You can always look at these for extra help later, okay? So let's go to the next page, and they have plenty of practice here. We're going to do several of these and just work them out together, solve the equation, check your solution. So I put a clean sheet of paper, 4 of those that we're going to work through, okay? And you can just follow along and write as we go through these. So the first problem says 24 minus 3m equals 5m. Do you notice how I have variables on each side of the problem? Okay, the first step, the first thing to focus on is getting all the variables on one side and constants on the other. And I misspoke. I really should check on one other thing. You should always try to simplify before you do anything else. Let's try simplifying. Really, simplifying is the first step. Can I take 24 and subtract 3m? And I hope you're saying, no, you can't. They're not alike. Okay, so I tried to simplify. I can't. So now I got to get all the variables on one side. So I tell you what, I'm going to add 3m to each side because that's going to put all my variables on the right and I'll have a constant on the left. So I hope I'm being clear here. In the book, I highlighted for you on the previous page that when you come across these problems, we have to focus on getting the variables on one side of the problem, constants on the other. I've accomplished that here. Now, when you think about your onion, this should be easy. We have a one-step problem to solve. I want to get m by itself. I have to get rid of the times 8 layer of my onion. So I'm going to divide by 8, and I'm getting m equals 3. Now I should check my answer. It's always good to take your calculator and check. You can verify that you have it right. To check it, you just do the following. You do 24 minus 3 times 3. And you see what you get. And then over here you do 5 times 3, and you see what you get. Both sides should be giving you the same thing. When you work this side out, you get 15, and when you work this side out, you get 15. Those are equal, so this is checking. 3 would be correct. Let's go to this problem over here. Okay. I see variables on both sides of the problem, so I want to move the variables on one side and put the constants on the other. Before I attempt to do that, let's try to simplify. Can I subtract these? No, I can't. They're not alike. Can I subtract these? No, they're not alike. Okay. Well, let's move all our variables to one side and our constants to the other side. Well, I'm going to move them. I want to get rid of the minus 2k. I'm going to move my variables to the left of the equal sign. So to get rid of a minus 2k, I should add 2k. And I can only add it to I got to add it to my like terms, which are the k's. So I'm adding it here. These cancel. I have 17 on the right. I have 9. And minus 3k plus 2k is minus 1k. Okay. Now, let me draw up my onion. Here's my center. Here's my next layer. The times negative 1 is the next layer. The outside layer, now this is a good thing that we're talking about this. The minus sign does not apply to the 9, it applies to the 1. So I got to treat this like I'm multiplying k by negative 1. The sign in front of 9 tells me what to do with it. Now, you might be looking and saying, you're nuts, Mr. Lemansky, there's no sign in front of 9. Well, yeah, there is. It's really a positive sign. When I don't see a sign, that means plus. To get rid of the 9 in front, I have to do whatever's the opposite of plus 9. Well, I hope you're thinking, oh, I got to subtract 9 then. To get rid of a plus 9, I got to subtract 9. So that's my next step. I got to take away the 9. So I have a negative 1k equals 17 minus 9 is 8. And now the next layer of the onion, I got to get rid of the times negative 1. So I should divide by negative 1 on each side. I'm getting k equals negative 8. Okay, I should check that. I should take my calculator now, and I should do 9 minus 3 times negative 8, and I should see what I get. If you plug this in your calculator, if I'm doing this in my head right, you ought to be getting 33 on the left side of this. And then over here, I ought to be doing 17 minus 2 times negative 8. And if I'm doing my mental math right, when you plug that in your calculator, you ought to be getting 33 also. You're getting the same thing on each side, so that's checking. That's correct. Let's try this one. Okay? We should always look to simplify. I noticed right away, wait a minute, I got variables on each side. I got to get the variables on one side. I got to move my constants to the other side. But let's try to simplify. I can't subtract 5z and 2, but look at over here. I have to distribute to simplify. So let's distribute. So I got the 5z minus 2 on the left. On the right, I have 6z minus, because positive times negative is negative, 2 times 4 is 8. Oh, I got my variables on each side. I don't want that. So to get rid of a plus 6z, I should subtract it. And I can subtract that from the 5z, so I have a negative 1z minus 2 equals negative 8. So now I'm thinking of my onion. Get that out of the way. Think of my onion. Z's the center, the times negative 1 is the next layer, and the minus 2 is the outside layer. I got to get rid of the minus 2 first. I'll add 2 to each side to get rid of the minus 2. Okay? Negative 1z equals, well, negative 8 plus 2 is negative 6. And then I can divide by negative 1 on each side, and z would equal 6. Now I should check myself again, so I should do 5 times 6 minus 2. When I do that in my calculator, I ought to be getting 28. And over here, I should be doing 2 times, parentheses, 3 times 6 minus 4. And when I put this in my calculator in the order I see it, I should be getting 28 again, and this is correct then. Okay? Over here, one more problem. I have variables on each side. I can't have that. I got to get them all on one side, but you notice I can simplify right here. Maybe I should highlight it. I can simplify here. I have distributing, so let's simplify first. And you can use your calculator, of course, when you do this. The 8y minus 6 I can't do anything with, but here, 2/3 times 6y is 4y, and 2/3 times 15 is 10. Okay, I cannot have variables on each side, so let's move. I'm going to move the 4y over here. To get rid of a positive 4y, I should subtract 4y. And I would get 8y minus 4y, and then we have the minus 6 equals 10. Okay, think of your onion now. Y is the center, the times 4 is the next layer, the minus 6 is the outside layer of the onion. I have to add 6 to get rid of the minus 6. It's supposed to be a 6 there. Okay, and I have 4y equals 16, and then I can divide by 4, and I get y equals 4. And then, again, I should check it. I'm not going to write this out again, but I ought to plug in a 4 here. I should plug in a 4 here and check it on my calculator to make sure these sides both equal each other. Remember, you must show complete work if you want to get full credit. What I am showing you here is what I want to see on paper. You do not have to draw the onion. That's just a visual of the concept I'm trying to get in your head right now. but I should see your step-by-step work if you expect full credit, okay? Moving forward, when you have variables on each side of an equation, there is a special thing that could happen, okay? The equations do not always have to have one solution. Every problem we've done up to this point in Chapter 3 has had one solution, and that's it. It is possible that you could have problems that are true for all values of a variable. That's called identity. That's a vocabulary word you should get in your notes. Identity means that all real numbers would be a solution. In other words, identity is saying I could plug any number I want for the variable and it's going to make the statement or the equation true. So instead of having one solution, any number would work. That's what identity means. On the other hand, an equation could also have no solution to it. Okay, there are equations out there that have no solution. And here would be a simple example of a no solution equation, like x plus 3. That's not a good example. Here would be an example. X plus 3 equals x plus 4. There's no number that I could put into x that's going to make this true. Like if I try plugging a 1 in here, I'm going to get 4 here and 5 here. Those aren't equal. Or if I plug in a 2, I'm going to get 5 here and 6 here. It doesn't matter what number I plug in for x. There's nothing I can plug in that's going to make this side equal to that side. Okay? So that's what I was trying to explain there. There are problems that could be no solution. Now, this next thing that I wrote out on my screen here, you should definitely put in your notes, this next statement that I have, okay? The only time you could have identity or no solution, these situations can only pop up if the equation has variables on each side of the equal sign at the beginning of the problem. Okay, in other words, if you have variables on one side of the equation only, you're going to get one answer for those every time. But if you have variables on each side of the problem, like the problems we're practicing now, these situations could pop up. So this is something you have to be aware of, okay? The only time I can get an identity or no solution answer is if the problem starts with variables on each side of the problem. So those 4 problems we just did on the previous slide, those problems all could have potentially worked out to no solution or identity. They did all work out to one solution, but they could have worked out to no solution or identity because the problem started off with variables on each side. Okay? Let's actually practice some more, and let's see when these situations pop up. Okay? Let's try these. Okay? Let's try a couple of these. This will demonstrate when these situations pop up. So you notice for number 8, let me write it up here, 9z plus 12 equals 9 times z plus 3. All right, I have variables on each side of the problem, and you notice on the right side I have to simplify. So let's distribute first. So I have 9z plus 12 on the left, and I have 9z plus 9 times 3 is 27 on the right. Do you notice how I have variables on each side of the problem? Well, I have to try to get all the variables to one side. That's my next step. So I'm going to get rid of the positive 9z on the right. So let's take away 9z. Now I want you to notice what happens when I take away 9z from each side. Now the variable cancels from the right, and I get 27, but you notice the variable also cancels on the left, and I get 12. Now look at this statement carefully. Does this make any sense? Could 12 equal 27? Think about that. I hope you're saying, wait a minute, Mr. Lemansky, that makes no sense. No, that's not possible. This is an example of a no solution problem. There is no number that I can plug in for z that will make the left side of this equation equal the right side. You would just write on paper after this work, after these steps, you would write underneath this, no solution. Now, Look at the start of the problem. Do you notice how I had variables on each side to start? When that happens, it is possible you could get no solution. Okay? Let's try another one. Let's do number 10. So here I have 3 times 2a plus 2, and that's going to equal on the other side 2 times 3a plus 3. Okay? Well, I got to simplify each side. I definitely have distributing to do, so let's do that. 3 times 2a is 6a, and 3 times 2 is 6. And on the other side, 2 times 3a is 6a, and 2 times 3 is 6. Okay, I have variables on each side. I got to get all the variables on one side. So I'll take away 6a from each side. And again, you notice what's happening here. The 6a's on the right cancel. I get 6. And on the left side, all my variables are disappearing. I get 6 on the left side. Now, that is a true statement. Okay, I can't solve for a. The a's disappeared. I'm left with a true statement. When your variables disappear and you're left with a true statement, this is a problem that I would write down identity. Now, identity means I can use any number I want and replace a with any number, and it will make both sides equal. I want to prove that to you. Let's pick 10. If I put a 10 in here, 2 times 10 is 20. 20 plus 2 is 22. And 3 times 22 is 66. If I put a 10 over here, I'm going to get 3 times 10, which is 30. 30 plus 3 is 33. And 33 times 2 is also 66. I can plug in anything I want, and it's going to make this a true statement. So you have to remember, when I'm going back to the first slide real quick, if you have a problem where we have variables on each side of the problem, it is always possible. Like when I look at this problem that they do in the book, when I see variables on each side, I have to be on alert that, hey, I could get identity or no solution to the problem. Now, the only way I'll figure out that is when I work it out. Now, this problem worked out to one solution, x is 2. So you could get one solution for your answer. It's possible to get no solution, or you could get identity. You have to do the work to figure that out. I'm going to stop the video here. If you have questions, make sure you ask during class time.